Okay, let's talk about mechanisms of reactions. Before we study our reactions in terms of thinking that reactants somehow gives us products. We go and even study this from the energetic point of view and relating it to kinetics through the Arrhenius equation. Basically, we said that if we go from reactants forming products, there's a certain amount of energy that the reaction will have to overcome that we call the activation energy, given here in Arrhenius equation, and then the higher the activation energy, the slower the reaction will proceed. But now, from the molecular point of view, what we can say is that in some cases, this reaction going reactants to products can go through a series of steps that we call elementary steps. So, for example, in this case, let's say that this reactant, instead of going directly to products, it forms an intermediate species that later on, this one will react in order to give you the final products. So now this one, by creating this extra reaction, really what we have now is two different steps for the overall reaction, and each of those steps, we call them elementary steps. So these elementary steps, each of them, 1 and 2 here, will have in principle their own activation energy associated with them, such that, remember that according to Arrhenius equation, if you have a different activation energy, then the rate of your reaction through the rate constant of your reaction is also going to be different. So in principle, the rate of the first reaction is different from the rate of the second reaction. And also remember that according to this, the higher is the activation energy, look at Arrhenius equation, the higher is the activation energy, the slower a reaction is going to go. So if it's really slow in a reaction mechanism, that's the one that we're going to be calling the rate determining step. So this rate determining step, it's always going to be the one that has the slowest rate or the highest activation energy. If your activation energy is relatively small, then the reaction will proceed relatively fast. But the one that is going to limit how fast the overall reaction can go is the one that is the slow reaction among all the reaction steps, the elementary steps that you are creating. Now, we can propose this mechanism, but how do we know that that mechanism is actually a good one in terms of the actual reaction that you have? Well, remember, mechanism is something that you proposed. It could be right, it could be wrong, but you have to prove that it's right. So now there are two main criteria that you have to follow in order to make sure that your mechanism is correct. The first one is that if you propose any elementary steps, when you add them up all together, they have to add up to the actual overall rate of overall reaction. So let's say that you have the first step, a reaction going to an intermediate. It's a slow step. The second reaction is the intermediate going into a product. When you add up these two together, what you know is that these two should give you the overall reaction, reactants going to products. Now, you can see that the intermediate in the first case, it's a product, but in the second, it's a reactant, so you can cancel them out. When you add up these two together, elementary step 1 plus elementary step 2, then you recover the actual rate, the actual reaction, the overall reaction, which is reactants goes to product. So the first case is correct for this particular mechanism. Now, the second one is that the rate law that you predict with this mechanism should be compatible with the rate law that you observe experimentally. So for that, what we have to take into account is that, remember, if we characterize or we know that one of the elementary steps is the slow step, is the one that has the highest activation energy, and because of that is going to be the one that we characterize as the rate determining step or the rate limiting step as well. So that's the one that we have to use to write down the rate law from my mechanism. And this rate law should be compatible from the proposed mechanism and the one that we have experimentally. So what we got from the experiments and the one that we get from these proposed mechanism should be compatible.